It is the 14th chapter in 11th standard physics. It is very important for you for this coming exam because this 10th unit, it comes under 10th unit of 11th physics. It has a 10 marks weightage for this coming course of the exam. And also it is important for next year also. You need the concept of this lesson in the lesson like electromagnetic waves and also alternating current. So you have to retain this concept in your brain for next year also. In this lesson, the first part of this lesson, we'll be discussing about the main points, the basic concept of this lesson, which are periodic motion, displacement variable, periodic function, simple harmonic motion, and characteristics of simple harmonic motion. The main characteristics of simple harmonic motions are amplitude, phase, initial phase, time period, and frequency. And first of all, we can discuss about what is meant by a periodic motion. We can see in our surrounding different types of motion. We are seeing the motion of vehicles, the flies moving, flying, and we have seen sometimes the oscillation of pendulum of a clock, or the children playing in a garden on swings. And also we know about the motion of the planets like Earth revolving around Sun, and even Earth rotates, spin about its own axis. So these are different type of motions. In these motions, some motions are periodic, some motions are not periodic. A periodic motion means a motion it will repeat after a regular interval of time. Example for periodic motion, we can consider the revolution of Earth. The revolution of Earth around the Sun, it takes 1 year, and every 1 year it will repeat again and again. And because of that periodic variation, periodic motion of the Earth around Sun, we are getting different seasons. At the same time, the rotation of the Earth, the spinning of Earth about its own axis is also a periodic motion, and it repeats in every 24 hours. So because of that, we are getting day and night. So any motion which repeats after a regular intervals of time is a periodic motion. This oscillation is a periodic motion. We have seen the oscillation of a pendulum of a clock. It repeats after a regular intervals of time. So this lesson will be discussing especially about oscillations and vibrations. Both oscillations and vibrations are periodic motion. Vibration means you might have observed sometimes the vibration of strings of musical instruments. The main difference, oscillations and vibrations are almost same, both are periodic motion. But one difference is in case of oscillatory motion, suppose we consider the oscillation of a pendulum. Oscillation of a pendulum. Suppose a pendulum is oscillating like this. In this case, there should be a restoring force which is always bringing the body back to the mean position. This is the undisturbed position of the body, the mean position of the body, and these are two extreme positions, A, B. And the restoring force here, when we consider the weight of the pendulum, mg acting downward, and if this theta is the angular displacement of the pendulum, then the weight mg can be resolved into two components. One component along this way, this angle also will be theta, the same theta. So this component will be adjacent side, so it will be mg cos theta. And another component is this one is mg sin theta. Mg sin theta. So always this mg sin theta is acting like the restoring force. It will try to bring the body back to the mean position. When the pendulum oscillates this direction, here also mg sin theta will act opposite towards the mean position. So it will try to bring the body back to the mean position. So here the restoring force is mg sin theta, that is due to weight of the body. And such a motion is called oscillation, in which the restoring force is provided by weight of the body. Here the component of weight mg sin theta is providing the restoring force, and which keeps the body oscillating. In case of a spring, if you take the case of a spring, suppose a spring is fixed at one point, one end of a spring is fixed on a wall, and to the other end of the spring we it's a wooden box, a wooden block, and if there is a frictionless table, and if you extend the spring, stretch the spring, move the block towards one direction, release, it will start vibrating. So when we move this block in this direction, the spring will get extended. Suppose X is the extension of the spring from the mean position. Then according to Hooke's law, the restoring force acting in the opposite direction, F is equal to minus Kx. This restoring force will try to bring the body back to the mean position. So here the spring will start vibrating and in that vibration the restoring force is due to the elastic property of the spring. So if the restoring force is provided by the weight of the body, the component of the weight here, mg sin theta, then it is called oscillation. And if the restoring force is provided by the elastic force, this minus Kx is the elastic restoring force, and then it is called vibration. So that is the basic difference between oscillation and vibration. In oscillation, restoring force is provided by weight of the body, and in vibration, restoring force is provided by elastic force, and both are periodic motion. Now we can see other important points here. The next important point is about displacement variable. In a periodic motion, the displacement variable has a wider perspective than the displacement we studied in one-dimensional motion. In one-dimensional motion, displacement means it is a straight line distance between the initial position and final position. In case of periodic motion, the displacement variable, it can be any physical quantity which changes with the time. A varying physical quantity with the time is called a displacement variable. So right now when I am talking here, my sound is traveling through the air. In that case, the displacement variable will be the pressure variation of atmosphere. When I am talking here, it is producing compression and rarefaction, and high pressure and low pressure, and that is moving in forward direction. So here the displacement variable will be the pressure variation in the atmosphere. It can be the electric field vector in case of electrical displacement in electricity, in alternating current. It can be the electric current, varying electric current in case of alternating current. And it can be even the normal displacement from the initial and final position. So any physical quantity which vary with the time is called a variable, displacement variable in this lesson of oscillation. Now we can see what is meant by a periodic function. An example for periodic function is y equal to a sin omega t, or y equal to a cos omega t also can be a periodic function. We'll see what is the meaning of a periodic function and what is the meaning of y equal to a sin omega t. We know that the motion of a particle in a circular path is an example of periodic motion. If it repeats again and again, it is a periodic motion. And such a particle is moving in a circular path here, and at an instant of time, suppose the particle is at A, and its position vector at this instant of time, suppose its position vector is OA, and that position vector is making an angle theta with the horizontal, so that we can resolve this position vector OA into two components. That is, the horizontal component will be equal to that OA cos theta, and this vertical component, this much will be equal to OA sin theta. This component is OA sin theta. So we can consider this displacement of this in the y direction, means the component in the y direction is y is equal to OA sin theta. OA is the length of the position vector of the particle revolving around the circular paths. Now we can see here, suppose initially we have got the equation y component. The y component is equal to OA into sin theta. Imagine the body started from the initial point here. When the body is at the starting point, suppose at the initial point I am taking the point P, and at that point theta equal to 0. If theta is equal to 0, then sin 0 is equal to 0, then y equal to 0. Means if I am plotting a graph for this motion of the body, if I take the y component on that y-axis, means the y component of this position vector on the y-axis, and theta on the x-axis. At theta equal to 0, when the body was at the starting point, at theta equal to 0, when the body was at the starting point, there was no y component was 0, because y equal to OA sine theta. OA is the position vector, and sine 0 is 0, so y equal to 0. Means we are at this point. There is no y direction displacement. Now, when the body start moving like this, we can see the y component is at this junction, y component is this much. Means the y component is increasing, and when the body reaches at this point, suppose that point is Q, at the point Q, the angle rotated is 90 degree, this total angle turned is 90 degree, and if you apply the equation, y is equal to OA into sine 90, sine 90 equal to 1 is the maximum value, so we will get y equal to OA. Means when the particle reaches at the point Q, the displacement in the y direction becomes the complete length of the position vector, that is OA itself. Means the value of y is keep on increasing. Initially it was here at 0. Then when the body start rotation, the value of y is increasing. And when it reaches at the point Q, it becomes complete position vector, because sine 90 equal to 1, y equal to OA. So we can see here the value of y gradually increasing and reaching a maximum value, and at this maximum point we can see here angle theta is 90 degree, and that corresponding value on the y-axis is equal to amplitude of the wave, amplitude of the oscillator. Now again we can see the bodies keep on moving in this direction, and when it reaches at this point we can see the position vector of the body of the particle A, that is OA. It is here now, and here also we can resort into two components. The x component, it will come, the x component will be this much, okay, that will be OA cos theta, and the y component is this much, that is OA sin theta. And when it reaches here, the total angle turn become 90 plus 90, is 90 plus 90, that is 180 degree. And sin 180, again if you apply the equation, y is equal to OA into sin 180. Sin 180 is also equal to 0, so y equal to 0. Means the graph will come downward like this. It is decreasing now, decreasing. Finally, when the value reaches, then angle turn become 180 degree. Again, sin 180 is 0, it become here. Means it reaches at the horizontal level where there is no y displacement. Displacement in y direction is 0. Again, it is keep on moving in this direction, and suppose it reaches somewhere here. At that time, the projection of this position vector on the y-axis, we can see here that is this much only. This much is the position vector, and when it reaches at the point here P, Q, R, S, when the particle reaches at the point S, we can see that the total angle turn become 90 plus 90 plus 90, that is 270. And if you apply this equation, y is equal to OA into sine 270. Sine 270 is minus 1, so we get y is equal to minus OA. Means the displacement become maximum in the downward direction, the full length of the position vector will come. So the graph is decreasing in the opposite direction, and at the angle of, this is 180 degree, and at the angle of 270 degree, it become minus OA, the amplitude become maximum in the reverse direction. Again it is keep on moving. We can see the component of the position vector is decreasing, the y direction component, or we can say the projection of position vector on the y-axis is decreasing. Now it is this much only. When it reaches here, this much only. When it reaches here, the total angle turn become 360 degree. When angle become 360 degree, we can see here y is equal to OA into sine 360. Then sine 360 is also equal to 0. So we can see the projection of the position vector on y-axis, it becomes 0 and the particle reaches here. So altogether, we can see in the graph, when it completes one full circular motion, the particle rotates 360 degree, then again it returns back to the 0 position. So what we are seeing here, when a body moves in a circular path, the position vector of that body, if you project it on y-axis, means the projection of position vector on y-axis means the y component of that vector, that is the vector into sine theta, that is OA sine theta. Initially OA sine theta was here and it started increasing in this direction when the body moves this way, and when the body reaches here it becomes maximum, and when again the body moves this way it is decreasing, and when the body reaches here it becomes 0, and when the body moves downward it is increasing in the opposite direction. At 270 degree angle it becomes again maximum. When the body moves this way it is decreasing, and at 360 degree it becomes 0. So what we can see here, the body moving in a circular path can be converted into oscillation of that body. Circular motion can be converted to oscillatory motion by taking the projection of position vector of the body moving in a circular path on y-axis, we can get the oscillation of the body. Or if you take the projection on the x-axis, again we can get when the body moves like this in a circular path, the OA cos theta will oscillate in this direction. And its value is changing periodically according to the angle. At 90 degree, the displacement in the y direction becomes maximum, and at 180 becomes 0, 270 opposite direction maximum, and this is again 0, and it will repeat again and again. So such a periodic motion is here represented by a sine omega t, because sine theta is a periodic function. Now we can see the important characteristics of SHM, simple harmonic motion. The first characteristics of SHM is amplitude. Amplitude means during the oscillation of a body, the maximum displacement towards one side, either towards right or left. If you take the waveform of the oscillator, you can see here when theta equal to 90 degree, the equation y is equal to a sine omega t. When omega t, that is theta, when it is become 90 degree, we can say sine 90 equal to 1. Then if omega t is equal to 90 degree, then sine 90 is equal to 1, that is y equal to a. That is called amplitude of the oscillator. That is a maximum displacement towards one side from the mean position. That is y become a when theta is equal to 90 degree, sine 90 equal to 1. That is called amplitude of the oscillator. Then the phase of the wave, if you represent a wave by using an equation y equal to a sine omega t plus phi, this equation represents a periodic motion, an oscillation or vibration. In this equation, the argument of the sine function, that is omega t plus phi, it is called phase of the wave. The value omega t plus phi is called, this is called phase of the wave. Phase. And if you know the value of omega t plus phi, we can locate where is the position of the bob of the pendulum. So that is why it is called phase of the wave. The stage of the oscillation at an instant of time, if you put the value of time and the angular velocity and initial phase, we can locate whether the bob is at the mean position or at the extreme position or anywhere in between the mean position and extreme position can be obtained if you know the value of omega t plus phi. So it is called phase of the wave. And again in that there is initial phase phi. Initial phase phi means at time t equal to 0, you can see here the phase of the wave become equal to omega into 0 plus phi. Then omega into 0 equal to 0, that is phase become phi. That is initial phase, it is a phase of the wave when or phase of the oscillator when time t equal to 0. That means, for example, suppose a small kid is playing on a swing. It is oscillating. And we know that the kid cannot start oscillation by itself. So its mother is giving an oscillation to the swing. So initially the mother is displacing the kid towards one direction, and after that she is releasing. So before releasing, before starting oscillation, the kid is already displaced through some angle from the vertical. That angle is the initial phase. From there onwards we start oscillation. So in the equation of oscillation we have to add that initial angle phi. That is the angle before starting the oscillation. Now if you consider the case of a grown-up boy, he can play on the string by itself. He can himself swing on the string. Then in that case, there is no need of any initial phase. Suppose the boy is starting from the mean position itself. Then his initial phase phi will be 0. Means if an oscillator is starting from the mean position itself, then the initial phase will be 0. If it is starting oscillation at an angle, from an angle, then there will be an initial phase. That initial phase is taken as phi in this equation. Then the fourth one is the time period of oscillation. Time period of oscillation means it is the minimum time taken for completing one oscillation, or you can say it is the minimum time interval in which the periodic motion repeats itself again and again. So here when we consider the oscillation starting from the mean position towards one extreme position and return back and go to the other extreme position, return back. That is called one oscillation. And the time taken for that one oscillation is called time period. Usually it is represented by capital T, and it will be measured in seconds. In this case, when a body completes one full oscillation, go to one extreme, then represented by this point, return back, again you come here, going to the other extreme point, it will become here, and the return back it will reach here. Means in one oscillation, one full crest and trough will be formed, means one full wavelength will be formed in one time period. Then the fifth one is the frequency of oscillation, that is represented by the letter nu. It is the number of oscillation or number of vibration in 1 second. So if you consider the time period and frequency, they are related by this equation. T is equal to 1 by nu, that is the reciprocal of the frequency is equal to time period, and also the time period is related to the angular velocity. We know that angular velocity omega is equal to theta by t. If we take a complete circular motion, a full circular motion or complete oscillation, the total angle theta will be equal to 2 pi, and the time taken for one full circular motion is called time period, or one full oscillation is called time period, that is small t equal to capital T, and substituting here we can get omega is equal to theta is 360, that is 2 pi radian, and time taken for one full circular motion is capital T, is omega equal to 2 pi by t, and we have here 1 by t is equal to 1 by nu, or we can say nu is equal to 1 by t. So nu is equal to 1 by t, frequency equal to reciprocal of the time period. Substituting here we can write omega is equal to 2 pi nu. So we have got two equations for angular velocity. In terms of time period it is 2 pi by t, and in terms of frequency it is 2 pi nu. So these are the important basic points which are needed for studying this lesson of oscillation. And in the next lesson I will be giving explanation for derivation of equation of velocity of an oscillator, kinetic energy, potential energy, total energy, and also some examples of simple harmonic oscillation like the pendulum and vibration of spring in detail. Okay.